Thank you, Václav and Thomas. Those were really great talks. We'll go ahead and move into our discussion session now. I'll start us off with the first question for Václav. You showed a map of seismic hazard and risk in Nepal with the latest high magnitude earthquake occurring in 2015. So is there an estimated earthquake cycle for the region or durations of time between major earthquakes recognized from the past? In other words, are there any predictions for when the next high magnitude earthquake could occur in this area?
Thanks, Delaney, for the question. Yeah, it's been always a question in seismology when the next big earthquakes are coming. So it's always hard to answer because even when we have estimates for sort of interseismic period, it may differ from earthquake to earthquake by a few hundred years. So for those very largest earthquakes in Nepal, those, for example, the one that occurred in the western part of the country in 1505, it has been estimated that it may be a few hundred years, up to 500 years or so, when it's expected that such an earthquake would happen again. And we know it both from paleoseismic records, and we know it from strain rates, from the motion of the Indian subcontinent, how it's moving with respect to Tibetan Plateau. And so it's very hard to say when it's going to happen, and it may still take another 200 years, but it is quite possible that one of those large earthquakes is going to happen in a relatively near future, whatever that means, because the strain rates or the strains that are the amount of energy that has been accumulated in that region is quite high, because the last large earthquake in the central and western part of the country occurred in 1505, and since then the energy wasn't really released, neither seismically nor in some kind of a slow motion. So there's been quite a bit of energy accumulated in that region, and it is possible that it will be released in relatively near future.
Great, thanks for that answer. This next question is for Thomas. There seems to be distinct patterns of landslide locations in the maps you showed. For example, they appear to trend in a dominant direction and cluster around certain areas. So how much of a role do you think the underlying geology or structure is playing in these landslide occurrences?
So in terms of the geology actually plays an important role. Most of that area has metamorphic rock, biotite gneiss and hornblende biotite gneiss, and when you look at the some of the cut slopes, you can actually see that there is weathering happening in some of the top layers, and that is playing a part in the landslide failures that are occurring in the region. The concentration of the landslides, especially in that northern part, is also tied to the presence of the overburden material and also the slopes in that region. And as we see from the rainfall pattern, you can see that the rainfall pattern within Idiki is also varies spatially, and that also plays a role. So geology plays a role, but it's a combination of the geology, the slopes, and the varying pattern of the rainfall that all contributes towards the spatial patterns of landslides that we see.
Great, thanks for that. Our next question is for Václav, that asks, are the sensors only measuring horizontal acceleration?
So the sensors are measuring acceleration in 3 components. So it's 2 horizontal components and 1 vertical component. So we have 3 component sensors.
Okay, thanks. And in relation to that, how are the sensors installed or data processed to prevent false positives?
So the sensors are installed. The installation of sensors is actually quite simple. So we have, as you could see the sensor on the picture, it's just a small box that can be mounted anywhere on the floor or on the wall. So usually we mount it on a wall next to a power outlet somewhere in we use governmental buildings most of the time. So there is quite a bit of false detections at a single station, because there has been also non-earthquake sources of disturbances and noise, like when someone slams the door or a truck passes by. So every single station has quite many detections. We are trying to limit the number of false detections at single stations by introducing machine learning algorithms for detection. So those can, to a certain extent, recognize whether it's an earthquake disturbance or some other kind of disturbance. So that's regarding a single station. And then regarding when we process the data, then of course we take into account multiple stations at the same time, and the processing method, it's like sort of a classical seismological algorithm that calculates the theoretical travel times from different locations as if it was an earthquake, and based on that virtual location of an earthquake hypocenter, it decides whether a few detections or set of detections make a meaningful sort of earthquake occurrence, whether a set of detections is an earthquake, or if it's just a random sort of cluster of detections that were not caused by an earthquake. So we use both, are trying to use both algorithms on the sensor or on a single station, and those algorithms that take into account multiple sensors. So in that case, when you have a detection at 5, 6, 7 sensors at the same time, it's very unlikely that it would be something else than an earthquake.
Thank you. Thomas, what role does different soil types have in the modeling of landslide susceptibility?
Yeah, so we are using a physical model for the landslide susceptibility modeling, and that is the reason why we are actually doing the electrical resistivity to characterize the soil properties in order to incorporate into the slope stability model. And the geotechnical properties of the soil play an important role for the slope stability. So that is critical to understand, and it is a difficult one to characterize for the entire region. So what we are trying to do is to do this electrical resistivity survey in some key locations and find how these parameters are related to the overburden material and the slopes, and see if we can actually come up with some spatial interpolation of the soil properties to be incorporated into the slope stability model.
Okay, so in relation to that, question asks, is any lab testing characterization of soil samples planned to determine shear strength, or is your focus mainly based on resistivity surveys?
We have not planned any lab testing. What we are doing is to do some field testing, like penetration tests and other methods to understand the soil properties using traditional geotechnical methods and compare that with the electrical resistivity.
Thank you. Václav, how does power work for the mountain stations, and what costs are associated with hardware in maintaining this system?
So the hardware and maintaining the station is relatively cheap comparing to other systems, I would say. So the sensors are the manufacturing price is something on the order of $100. So that's the cost of the components. And then once we deploy the sensor ideally lives its own life without any maintenance. So we can check the status of the sensor online, and when it's not running, it's most likely because there is some kind of an outage, either a power outage or internet outage, and it comes back online when these resources are again available. And for those sensors that may break in future, we are hoping to get at a point. We are not at that point yet, but we are hoping to get to the point where sensors would be so low cost that it would not be really feasible to, or it would not be really beneficial to go out there and maintain them, that we would have just such high number of sensors that would be that low cost that we would not really have to maintain the sensors in the field. However, right now we do that, and I will do it with a few sensors right now on this Nepal trip. So those costs are relatively low, but they depend on strongly depend on the location of the sensor. So when the sensor is just a few hours drive, it's going to be a cost half a day of a person. But then once they will be deployed somewhere higher up in the mountains, that may take a longer time, and the costs associated with that will be larger too.
Great, thank you. Thomas, a question for you asks, what are the reasons that the GPM precipitation data would be different than the rain gauge data? I know you touched on this a little bit, but I don't know if you can speak to that a little more.
That's actually if you look in the literature, you can see that there are other studies also verify that in mountainous regions that the estimates, rainfall estimates from GPM is actually significantly underpredicts the actual rainfall. So our work just validates what others have found, and it is because of the orographic effects that are there in the mountainous region, and that really shows the need for more denser rain gauge networks in these regions to be able to get an accurate estimate of the rainfall.
Great, thank you. Václav, there's another question that just came in that asks if you could explain the smart alert that you touched on in a little bit more detail.
So the idea behind it is that we are using, as we are using cloud service, we are using a pops up publish subscribe system on the cloud that different services can sort of subscribe to and get the information that they want. So there's actually multiple different alert devices, let's say in the future, that can subscribe to the system and get the information about the earthquake or about something else that they're interested in. So this is a component that we actually concentrate the least on right now, honestly, because we are more on the technological side of developing the sensor and the cloud platform as a whole. And we are hoping that, for example, in Nepal, the alerts are going to be distributed on sort of a national level via systems of institutions that can integrate these maybe better than we can. But the idea behind it is that systems can subscribe to this publish subscribe system on the cloud and yeah, receive alerts that way.
Great, thanks for that. Another question for Thomas. In your analysis of geotechnical properties, does using electrical resistivity provide accurate water content measurements at depth for deep-seated landslides?
In our initial analysis of the electrical resistivity data, what we see is low resistivity regions actually matches with the areas with the higher water content and lower strength. So that's what we have seen in our preliminary analysis. And we are right now working on quantifying the strength properties.
Thank you. Another question for Václav. Is your early warning system also investigating precursor events such as swarms of small earthquakes or foreshock?
So there is very limited capacity, unfortunately, for us to investigate foreshocks and stuff like that, because the sensor has quite a bit lower sensitivity than sensors that are typically used in seismology, that are much more expensive, but also much more precise. So our sensor can detect an earthquake from about magnitude 3.5 and larger than that. So foreshocks that are typically, well, we may have foreshocks that are larger than this, but many foreshocks and many very small events that may occur before a large earthquake, they are smaller than this. So we don't really concentrate on this, and these sensors are really targeted at those very large events or events that are larger than magnitude, let's say 4.
All right, great, thank you. So Thomas, does the proximity to stream drainage paths or tributary channels show any correlation to landslide occurrence?
In the 2018 event, there was also a major flood that occurred. And what we saw was due to the flooding in the streams and undercutting of the slopes, there were some slope failures occurring on stream banks. But one of the major stressors for landslide in the Idiki is the anthropogenic activity, the cut slopes, and also the buildings. And this is also something that I want to point out. That is one factor why we have a lot of those landslides happening in that central portion of Idiki and not much in the north and the south, because in the north and south we have forests that have not been disturbed. So that the anthropogenic activity is a major stressor for landslides.
Thank you. Another question just came in for Václav. It asks if electrical failure, for example, off at night or as a result of system failure due to an earthquake, how can you keep track of aftershocks?
So keeping track of aftershocks would be definitely challenging because of those outages. So we are limited by these things, and we will be, because when we are designing a system that uses these resources that are already there and doesn't set up any new like our own, for example, satellite internet connection or our own electrical sort of supplies and batteries, we can do things quite a bit more cheap or quite a bit more low cost, but we are definitely dependent on these. So what I'm hoping for, and of course it may be for every earthquake, it may be different, but the data show from the 2015 Gorkha earthquake that the internet outages of cell, for example, cell internet wasn't as widespread as one would think. It was only about 15, 20, 25% based on the data from Ncell provider. So I'm hoping that even after a relatively large earthquake, we would still have a decent coverage to cover aftershocks. But of course, it's going to be challenging. So for us, we really target the system on the strong earthquake, and then definitely we will have some outages and stuff, and we will not be able to provide the data quality that an independent seismic network would be able to do. But on the other hand, we are able to do things quite a bit cheaper.
Great, thank you. Okay, we're almost out of time, so I will go ahead and ask the last question to both of you. What are you looking forward to most in the next phases of your work, and what are you hoping to accomplish from this?
Thomas, do you want to go first?
Sure, I'm happy to. So in our next year, our target is to actually get this early warning system operational in Kerala, and have that transferred to the Kerala State Disaster Management Agency to provide the alert to the community. And we hope we can actually make that possible, because that would be a great resource for the community, and especially this community depends on rain for all the tea gardens and everything, but at the same time rain has become a fear in the community because of all the landslides, and we hope that we can actually support this community through this effort.
So what I'm looking forward to is also a few things. I'm looking forward to, right now, actually, I'm in Nepal, and we are starting the second phase of the project in about 10 days. And we are heading up to the higher mountains on the north of the country. So it's going to be beautiful out there. So I'm looking forward to that. And also, and more importantly, I'm looking forward to collecting important data up there about the connectivity and latencies, because that's we have already tested now that on the southern part of the network it works quite well, but the reality of internet and power connection may be quite different in the north of the country. So I think that in the next year we will learn quite a bit more about how the network is feasible in this very high mountains regions, and hopefully it's always hard to be seismologist, because I'm wishing some earthquakes to happen so we have something to see in our data. But of course, I'm not wishing any strong earthquakes on Nepal, but I'm hoping to record some magnitude, let's say low 4 earthquakes, so we can get some real earthquakes in our system.
Great. Thanks for those answers. Well, that's about all the time we have for today. If you have any questions that were not addressed, you can email us at webinars@americangeosciences.org, and we'll make sure to send your questions along to the speakers. Thank you again, Václav and Thomas, for sharing your time, expertise, and insights with us today. Thank you everyone for joining us. We look forward to seeing you next time.